Hello everyone, my name is Jingyi and welcome to my talk on SAM, database generation from query workloads with supervised autoregressive models. This is a joint work with researchers from NTU, Alibaba Group, and ByteDance. Nowadays, users are increasingly adopting the use of cloud databases. Before migrating data from local to cloud providers need to benchmark different DBMS on the user's database to recommend a product. However, cloud providers usually don't have access to the user's data at this stage. On the other hand, cloud providers may have access to the user's query logs and collect a set of queries and the result cardinalities, that is, the size of the result. For example, here's a query and the result cardinality. The query tries to find all the people who are aged above 40 and has a salary of more than 50,000. One important point is that queries and the result cardinalities provide information on the data distribution. For example, with a given query and cardinality, we have information on the cumulative density of a particular region in the data space. As a result, we can leverage the query workloads to generate a synthetic database with similar data distributions. Benchmarking can then be conducted on this synthetic database. Another use case of database generation is stress testing for databases with strict access controls. For example, core user database of a social media or e-commerce platform. Replicating the entire database for stress testing is highly restricted for those databases. So similarly, one can first collect a query workload, generate a synthetic database from the query workload, and then perform stress testing on the synthetic database. Now let's look at the problem setup. The problem of database generation from query workloads is formally defined as follows. We consider a set of m queries Q and their cardinalities K collected on a database. We aim to generate a database that satisfies the cardinality constraints and is close to the original database. We use the cross entropy between the discrete data distribution of the generated relation T head and original relation T as a measure of closeness. There have been some previous research work on this problem, and the problem has been proven to be NEXP complete, which means that we can only design efficient approximate solutions to the problem. Existing work proposed a method based on probabilistic graphical models, or PGM, to solve this problem, but it has a number of limitations. First, it has a potentially inaccurate data modeling because of the independence assumptions that it makes. It is poorly scalable and has low fidelity on multi-relation databases and joint queries. With those problems in mind, we present the goals and solutions of our approach. The first goal is the training of an accurate generative model from cardinality constraints, so we can generate the database by sampling from the generative model. To this end, we propose to train an autoregressive model of the joint data distribution. The second goal is the efficient processing of large-scale query workloads. We propose to use a technique called differentiable progressive sampling to train the autoregressive model. The third goal is the effective and efficient generation of a multi-relation database. We propose two techniques, inverse probability weighting and scaling, to generate a multi-relation database. The final goal is assigning join keys to generated relations with high fidelity. We use a group and merge algorithm to assign the join keys. We'll discuss each of the goals in detail. First, let's look at the workflow of SAM. SAM is a query-aware database generator based on autoregressive models. SAM consists of two stages, learning stage and the generation stage. At the learning stage, SAM efficiently and accurately learns the joint data distribution using differentiable progressive sampling. At the generation stage, with the supervised autoregressive model, we generate a high-fidelity database from the autoregressive model using inverse probability weighting and group and merge algorithm. Now let's move on to our first goal, training an accurate model. SAM learns an autoregressive factorization of the joint data distribution into the product of a set of conditional probability distributions. For example, if we have a relation with n columns, then we can model the joint distribution Px1 to xn as a product of the conditional probabilities Pxi given x1 to xi minus 1. The biggest advantage of the autoregressive model is that it does not make any independence assumptions. For a multi-relation database, our model learns the joint distribution of the full outer join. We learn a set of additional virtual fan-out columns in the full outer join, which indicates the number of times each primary key is fanned out, that is, the number of foreign key relation tuples it joins with. For example, if we have 3 relations with the primary key of relation A joins with the foreign key of relation B and C, then in the full outer join, we'll insert 2 virtual fan-out columns. Now moving on to our second goal, how do we efficiently train the autoregressive model from the query workloads? SAM leverages a technique called differentiable progressive sampling, which is from existing work on cardinality estimation. Here is how differentiable progressive sampling works. So if one has a deep autoregressive model of the joint data distribution, a technique to predict the cardinality of a query is called progressive sampling, which works by progressively sampling in-range values from the conditional probability distributions. If we replace the sampling step by the combo softmax sampling operator, we make the entire process differentiable. So we can calculate a supervised loss, or Q-arrow, between the predicted cardinality and the true cardinality, and backpropagate this loss to train the deep autoregressive model. Differentiable progressive sampling has a linear time complexity, so it is scalable to large-scale datasets. With the trained autoregressive model, let's discuss how do we generate a database from the autoregressive model. Let's first look at the case of generating a single relation. So given an autoregressive model of a single relation's joint data distribution, we can simply generate a relation by uniformly sampling tuples from the autoregressive model. Here's how the sampling process works. The autoregressive model will first output the unconditioned probability of x1. We sample a value from this probability and feed the encoding of this sample value into the autoregressive model to get a conditional probability of x2. We sample x2 and feed it into the model to get a conditional probability of x3. And finally, we sample a value of x3. So now we have obtained x1, x2, x3, which is a uniform sample of the joint distribution. The sampling process can be batched over multiple GPUs and is therefore highly efficient. There are more questions we need to consider if we move on to the generation of multiple relations. One of the biggest difference is the fan-out effect. So due to the fan-out effect, the distribution of base relation tuples are different in the full outer join compared to the distribution in the base relations. For example, if we look at the tuple 2m, in the original relation A, it appears 1, so the probability is 1 over 4. But when it joins with the other 2 relations B and C, it is fanned out 4 times in the full outer join. So in the full outer join, the probability of the tuple 2m is 1 over 2, which is different. So the problem is, how do we generate unbiased samples for base relations? Here, we apply a technique called inverse probability weighting to adjust for this fan-out effect and generate unbiased samples for each base relation. The basic idea is that given a full outer join tuple X, we associate the derived tuple for base relation T with a sample weight. The sample weight is the inverse of the total number of times the derived tuple for relation T is fanned out during the full outer join. We also propose a scaling technique to avoid sampling a huge number of tuples because the full outer join size is usually huge. With a scaling technique, we first sample a small set of tuples and scale the weights so that the weight sums to the base relation size. The details of these 2 techniques can be found in our paper. Now let's discuss the final goal, the joint key assignment. So let's first look at the two types of data correlation in a database. The first type is the intra-relation data correlation, which refers to the data dependency across columns in a single relation. The second type is the inter-relation data correlation, which refers to how tuples from different relations are joined together. Note that the interrelation data correlation is captured by the join key columns, but as we are using an autoregressive model, the join key columns cannot be explicitly modeled in our model. So how do we assign values to the join key columns in the generated relations? An intuitive idea is to randomly assign the join keys. So assume we assign the primary keys sequentially and assign tuples in the foreign key relations with a random key. We may end up with generating a database with a totally different join result. For example, if we look at the generated relation on the right here, where we randomly assign the join keys, we may end up assigning the foreign key 1 to all tuples in relation B and the foreign key 2 to all tuples in relation C. This produces an empty inner join result. So there's no way the generated relation can preserve the input cardinality constraints. So to address this issue, we propose a group and merge algorithm that leverages a necessary condition for other join tuples to share the same join key. Again, due to the time constraints, if you're interested, you can find the details in our paper. Now let's move on to the evaluation. We evaluate database generation methods in 3 aspects. First, fidelity of the generated database to input cardinality constraints. Second, closeness of the generated database to the original database. Third, efficiency of the processing and generation process. We compare our method with the baseline method, which is based on probabilistic graphical models. We use 3 datasets, 2 single relation datasets, DMV and census, and a multiple relation dataset IMDb with a photo join size of 2 times 10 to the power of 12. So for the evaluation of fidelity, we find that SAM significantly outperforms VGM in terms of fidelity on IMDb. Fidelity to input cardinality constraints remains high when scaling SAM to a large-scale query workloads with a size of 100,000. Existing methods, the method based on probabilistic graphical models, can only work on a database on a query workload with a size of 400. The second evaluation is on closeness. SAM generates a database that is closer to the original database and can well generalize to unseen queries, achieving 300 times less mean error on IMDb when tested on a set of independent test queries. For the evaluation on benchmarking, we measure the query latency of a test workload on the original relation and the generated relation. The query latency of the database generated by SAM is much closer to that of the original database. SAM achieves 20 times smaller median performance deviation on IMDb. For the evaluation on efficiency, we find that the processing time scales as a high degree polynomial for probabilistic graphical models, but linearly for SAM. Therefore, SAM can process query workloads of a much larger scale. In conclusion, we consider the practical problem of database generation from query workloads, which has wide application in benchmarking and stress testing. We propose SAM, which accurately learns the joint data distribution using a single autoregressive model. SAM efficiently and effectively generates multiple base relations using inverse probability weighting and scaling. SAM assigns join keys using the group and merge algorithm to achieve high fidelity. We conduct comprehensive experiments to show that SAM significantly outperforms existing methods in terms of data fidelity, closeness, and efficiency. Here comes to the end of my video. Thanks for watching. If you have any questions, you can reach out to me through the email here. Thank you.